And this is the forward, backward, and then this is the laser pointer. So we have Jason Eastman give an introduction to EXOFAST V2.
All right, everybody can hear me? Great, I'm very excited to tell you about EXOFAST 2, which is, as Elise mentioned, a generalized package for publication quality global fits of exoplanets. So it can do just the star, it can do just transits, it can do just radial velocity, or any combination of them. And this is just a nice animation of what a transiting planet looks like, and then a model of isochrones that it uses to fit. But before I get too far into it, I want to thank all of the expert helpers that are going to be with us tomorrow. So these are the people that you can ask questions to in addition to me if you run into trouble. And in particular, I want to thank Joey, who's been a huge help over the last year in particular in breaking EXOFAST over and over and over again, and ultimately making it far more robust here for us today. So thanks to this whole team and for everybody who's been organizing this, especially Elise, who's been a huge help in all of this. Okay, so EXOFAST has been a pet project of mine for about a decade. And in 2013, I published the first version of EXOFAST that could model, it used a differential evolution Markov chain Monte Carlo to model a system in a globally consistent way. So it modeled the star and a planet with transits or radial velocities. And it did it in a nice globally self-consistent way. Unfortunately, the original version really only modeled a very specific scenario that in the end, it only did a fixed ephemeris, so you couldn't include transit timing variations. It only did a single wavelength, so if you had multiple observations from multiple telescopes and multiple bands, you just had to fit them in piecewise or assume that they all have the same wavelength or the same limb darkening. It could only do a single planet, so if you had a multi-planet system, you just had to do them independently. You could only do a single radial velocity instrument, so if you had observations from Keck and observations from high-res, you either had to put them on the same system and then just sort of ignore the offset that might be there, or just write your own thing. And it really only did like solar type stars. It was limited to maybe 0.5 solar masses and above if you really pushed it. But in the end, it was a good start, but you really couldn't do many realistic data sets with this. So if this is, I just want you to have like an intuitive feel for the improvement here. So this is EXOFAST version 1. It's nice, it's pretty shaded, looks cool. But this is what EXOFAST 2 is. It's in color, it's got multiple planets, multiple transits, simultaneous transits. You can see some going really fast, some going slow. It's just prettier with the font. Even the font's better. Just like everything about it is just much better. And so it took me about 5 years to get from one to the next, but it's a huge improvement. And I just want to sell you on this. So whereas EXOFAST V1 can do a very limited set of realistic publishable quality fits, EXOFAST 2, I haven't encountered a system that I couldn't fit with it. So I'll show at the end systems that we can do, but it's totally public, and I think you can model basically every type of system that you want to do in a publication quality global model. So this will be my summary slide. So and this is basically an outline for the rest of the talk, but I just want to run through some of these points in more detail here. So I'll just skip over this, but we'll come back to that. But if you want to, you can download it right now today on GitHub. And even though it's written in IDL, which is the #1 complaint that I get from EXOFAST, you actually do not need an IDL license to run it. I distribute a pre-compiled version, so you can run it without an IDL license at all for free. Okay, so before I get into the details of what EXOFAST 2 can do, I want to just take a step back and since this is all students, we may have lost you at differential evolution Markov chain Monte Carlo. That's quite a mouthful. So what is Markov chain Monte Carlo? I could spend an hour or a week just talking about Markov chain Monte Carlo. I've got 30 minutes here, so I'm going to spend about a minute on it. Excuse me. So briefly speaking, you just throw a bunch of chains, or sometimes you may have heard them called walkers. Those are the same thing. It took me a long time to figure that out, but same thing. So you just imagine that we have a parameter, let's call it the semi-major axis, and another parameter, let's call it the depth. You just scatter a bunch of chains that start in different regions of that parameter space, and then they all just take a step randomly. And you compute a model based on the initial step, and you compute a model based on the random step that it takes, and then you compute the residuals effectively. The residuals from each model, and you sum those residuals, and the smaller the residuals are, the more likely that model is. And then it just basically, if the residuals are smaller, it's more likely to step there. If the residuals are larger, it's less likely to step there. And so if you do that thousands and millions and maybe even billions of times, you start to get this, it starts to map out this region, and it'll start over here, and it says, oh, that's not actually that very good of a model, and it'll converge into here where this is actually the best region of parameter space. And then you cut out that original, that starting point, that's called the burn-in, because you don't want that to bias your results, and you end up with this posterior probability distribution function. So if you look at that in one dimension now we'll just consider that it's the quantity A over R star, the scaled semi-major axis. And I just take a histogram of all of the values where it steps. You end up with this nice histogram, and generally speaking, it looks like a Gaussian distribution, but it doesn't have to. Sometimes you could have a bimodal distribution or something with a long tail. It's literally just saying, this is how many times I stepped here, and I stepped here in proportion to my likelihood. That's really all you need to know about MCMC. It's just a fancy way to map out parameter space. That's it. And so to give you just sort of a more intuitive feel, you can kind of see the more steps you take, the more accurate you are in mapping out that posterior distribution. So if you take a few steps, you get a decent idea of where the parameter is. You can see when it loops over again. It's still pretty close to here-ish, but it's kind of broad, it's kind of spiky. Maybe you don't really know it that well, but when you start taking more and more steps, it looks more and more smooth and Gaussian. And that's what we say when we say converged or well mixed. It looks smooth, and it's a good representation of the posterior distribution. Okay, so that's all I'm going to say about MCMC. You can get a lot more complicated, but we won't. Okay, so now I'm going to go into some of the details about EXOFAST v2 and some of the detailed features of what it can do. So I said that the original EXOFAST could only go down to like 0.5 solar masses. If you're pushing it, 0.6 is more realistic. One of the major advances in EXOFAST v2 is that we implemented the missed stellar isochrones, and that's a new isochrone package that Vespa also uses. It was first published in 2016, but the major advance of that is that it goes down to 0.1 solar masses. It does stars from 0.1 to 300 solar masses, and so now you can do all of the M dwarfs that TESS and K2 and everything is finding for the host stars. And again, just like the original EXOFAST, it models it in a nice self-consistent way, so that you model the star and the planet at the same time. By using the missed stellar evolution, or the missed stellar tracks, you then encode all of the physics of stellar evolution that people know way better than I do. I just steal that from them, and then we just inherit all of that knowledge basically for free. We just interpolate isochrones, and we get a very good stellar model. And we just do that by we independently draw from these stellar parameters, and then we penalize it for basically the distance between the stellar model in this red asterisk and our point that we draw in our MCMC. We just add a penalty term to our likelihood function that says, hey, you can't be too far from that isochrone, or you're not a physical star. So here, this is within the uncertainty of our point, or maybe even in the model that then guides it to that isochrone. Okay, but then another huge advance of EXOFAST v2, again dealing with constraining the star, is we now incorporate K. von Stassen's code that models the spectral energy distribution, or the SED, of the star. And this is actually This is hugely important in the age of Gaia. So now that Gaia has flown, we have basically, we know the distance to every planet host now, or that any of us will likely conceive of in our entire careers. We know the distance very well to all of those billions of stars. And all of them are bright enough that that we can't really imagine going any fainter for the kinds of work that we do. So that's huge. But on top of that, we already had catalog photometry for all of these stars. So these 3 points here come from the WISE survey. That's an all-sky satellite, or all-sky survey. So basically every planet host that you can ever imagine now or in the future already has this WISE photometry. Similarly, this is 2MASS, all-sky survey. We already have all of that catalog photometry for everything. This comes from, actually this is Galax. That's also an all-sky survey. You might not want to use that most of the time. You can see there's actually quite a big difference between the data points here and the model there. And that has to do with the unreliability of the model itself. But then we also have APAS magnitudes or even Gaia magnitudes for the optical band. And again, those are most stars have those photometries. So that combination with the very precise distances from Gaia and the observed fluxes from these catalog photometry, or from the catalog bands, gives you a very precise stellar radius. So basically the normalization of this curve, or the integrated flux here gives you the bolometric flux of the star. And then the normalization of that is set by the quantity, the radius of the star over the distance to the star squared. If we know the distance from Gaia, we get the radius basically for free for every star, every host star of every planet. So to about 2%. That's huge. This was not the case 4 months ago. That's amazing. And it's going to be huge going forward. Okay, so why do we bother doing the stars fitting the stars simultaneously with the planet? You know, you could do it separately, fit the star, and then derive it after the fact. But the cool thing about transits is that you can actually constrain the stellar density from the transit itself. And normally I don't like to show equations. When I see them in talks, I usually glaze over. And if you're that type of person, feel free to glaze over. This isn't that important. I just want to show you that it's super easy. The transit actually constrains the stellar density of the star. That's the point of this slide, but I'm just going to go through the very simple algebra to show that, because that's not an intuitive thing to say. Why would a transit constrain the density of the star? So you just start with Kepler's equation, and I multiply by the factor of 1, r star squared, or r star cubed over r star cubed. That's all I've done, and then I regroup it. So now I have a over r star, excuse me, a over r star cubed, and a over r star happens to be an observable. It's basically the duration of a transit. So I can say I know this when I observe a transit. And now you see that this quantity here is just 4. I think I know the value of 4 pi. I know the value of pi g. I know that. And then this quantity m star over r star cubed. That's just the inverse of the density. So I can actually regroup, and I can say, if I just measure this, and the period here, I know the period from the frequency of transit. So I know a over r star from the duration of the transit. I know the period from the frequency of transit. I know these because they're constants. And the stellar density just falls out. And so when you observe a transit, you get the stellar density for free. And so if you can constrain the stellar density from the transit, you should really model the star as a global system, because that can feed back into the properties of the star, which then feed back, as Raphael and basically everyone keeps saying, know thy star, know thy planet. If you know everything about the star depends, or everything about the planet depends on the star. So the better you can constrain the stellar parameters, the better you can constrain the planetary parameters. And when you do this all simultaneously, it feeds back to one another. So you can improve, the transit can improve the stellar parameters improve the planetary parameters. And ultimately that's what we care about, or at least that's what I care about. Okay. Oh, and another thing that is, so most of my talk here is going to be about once you've basically validated the planet, you want to get the stellar parameters out, or the stellar and planetary parameters out as accurately as possible. and I've basically assumed that you've done the false positive vetting, you've already run VESPA. But one thing that you can do when you model it this way is when you get this stellar density out, you can compare it with the known stellar density from other sources. So you know the Gaia radius, you probably have a spectrum, or you might have a spectrum from somewhere else, or some other source of the mass from which you can calculate a stellar density. And you can compare the density that you infer from the transit and the density that you know from the star. And if those are very discrepant, that might be indicative of a false positive. So that might be another scenario where you could do some false positive vetting and say, maybe this isn't so real. So that's another big advantage of being able to model the star and the system as a whole self-consistent physical system. Okay, so now I'm going to go into more of the details of EXOFAST 2 and what it's capable of doing. So I showed you earlier that it can do multiple planets. So it can actually do an arbitrary number of planets, including 0. So if you want to model just the star using the isochrones or the SED formalism that I've created here, you can do that. You can model it. There's 4 different ways to constrain the star, or actually more than that if you want to be, or if you really want to start counting. But you can just apply that to if you just have a star, maybe you don't even care about planets at all. You can just model the star if you want, but you can also model as many planets as you want around it. So one of the things that I see a lot of people do when they fit multiple planets is they fit them independently, and they don't use the fact that each transit implies its own stellar density, and that stellar density doesn't change depending on which planet you're around. So one of the advantages of EXOFAST V2 is that I don't actually fit A over R star. It's not a parameter that I fit to each planet, because it's actually totally it's over constrained, because I fit the mass and radius of the star, and I fit the period of the planet. And with Kepler's law, which is included, I can derive the semi-major axis, and I already have R star. So it's a totally derived quantity for each of the planets. I just give it a period, and now I know the duration that I expect, basically. With multiple planets, you can also get tighter constraints on the eccentricity. So you can say it's probably not dynamically stable if the planets are crossing one another, if their orbits cross one another. So I can just throw out any solution that has an orbit crossing, and then that automatically constrains the eccentricity a lot better. One of the major problems that I'll talk about on Friday's talk, when I talk about more details about fitting transits and radial velocities together, is this big problem about eccentricity in transit-only light curves. But I don't have time to get into that today. And as you can see here, you can do simultaneous transits. EXOFAST V2 cannot do overlapping mutually transiting. So if you have a transit that actually crosses a different planet and they mutually eclipse each other, it can't do that. But the a priori likelihood of that is quite small. So it just sums the flux decrement from all of the transits simultaneously, but it does that seamlessly. And you can see here that the model will include both transits simultaneously eclipsed by the star. In addition, it includes transit timing variations, transit duration variations, and transit depth variations that you can turn on and off individually for each star. It does not then feed back into the dynamical model that Dan Fabricate was talking about, but then you can feed that, you can use those results to feed back into something like GTV-FAST if you'd like. Okay, so you can also do an arbitrary number of transits. So EXOFAST V2, this was used to fit Kelt 6, Kelt 6. This is 16 different transits taken from probably a dozen different observatories, and each of them you can see I think there's 6 or 7 different band passes. Each of those, so there's a couple of V-band transits. Those are modeled with the same limb darkening parameters because they're both V-band transits, but the G-band transits are modeled with different limb darkening parameters corresponding to the G-band. And so similarly, all 16 transits have self-consistent limb darkening parameters that are consistent with each of the transits, but according to their own limb darkening laws from the filter that it was observed in. You can have an arbitrary number of detrending parameters that you include with each transit. So they can vary. You could have 3 detrending parameters with this one because it was super noisy, and you can have 0 with that one, or whatever. Any mix of detrending parameters you can have for any of the transits. We can also model secondary eclipses, thermal and reflected light, or dilution. So in the era of tests, you're going to have a lot of stars that are going to tend to dilute the light curve, and you can include that dilution term when you model it on a light curve by light curve basis, or on a filter by filter basis. You can have, so I mentioned earlier that the original version of EXOFAST could only do one radial velocity instrument. Now you can do an arbitrary number of radial velocity instruments. And so these, each new instrument is now modeled with its own 0 point, so it can be offset arbitrarily, and that's a fit offset, and it also has its own jitter term. So oftentimes you have a stellar jitter or an instrumental jitter that you fit to make sure that the chi-square per degree of freedom is 1 effectively. So each new data set fits its own jitter and 0 point, but then has the same consistent eccentricity and planetary properties. And additionally, you can also optionally fit a linear trend that might be indicative of a long period planet that you haven't observed yet, or maybe even a quadratic trend that you can't really constrain a full period for, but you know that it's there. And then one of the really nice outputs, this is the final outputs that it creates is the LaTeX source code for this table here. So it will automatically summarize the probability distribution function. It'll take the median and 68% confidence interval, and it'll summarize it. It'll round to 2 sig figs in the uncertainty, and it'll round the median value to the same level of significant figures, and it'll generate the source code. This was totally untouched, generated directly by the code. Another nice feature is that it incorporates the Chen and Kipping mass radius relation, but only if you want it to. So if you're only fitting transits or you're only fitting radial velocity, you can then use the Chen and Kipping relation to derive the masses or the radius of the planet so that you can predict properties. So the use case that I see most obviously for this is I'm looking at a test light curve, and I want to see, or I fit it, I see its radius, and I want to see, that's a really cool target. Maybe I want to do some radial velocity follow-up on that. What is the semi-major axis that I would, or the RV semi-amplitude of that system that I would predict? And it would say, I predict 3 meters per second plus or minus 2 meters per second. You can say, that's doable. I might do that. Or it might say 1 millimeter per second plus or minus 1 meter per second. You're like, okay, that's probably not worth my time. So it'll just automatically do that for you. And I'll put that in that same table. And another thing you can do is apply priors on any fitted or derived quantity. So if you want to fit, or if you have, for example, the biggest use case I can think of for this is a Gaia parallax. So it incorporates the distance, or it fits the distance. If you put a prior on the parallax, it will then constrain the distance that it fits. You could also, if you don't like the missed stellar isochrones for some reason, you can put a prior directly on the mass and radius of the star and ignore any of the stellar physics that I've got in there. Or if you have literature values that you want to include directly, you can do that. So I think the real power here is in the upcoming era of tests. Soon we are going to have a lot of data from tests, a lot of high quality data. And if the community can rally around this code, I think it's a relatively straightforward code to use for as sophisticated as it is. We can really present a homogeneous analysis and characterization for all of these systems rather than a hodgepodge mix of parameters. And that will certainly make Julian's life easier at the EXOPLANET archive when he collates all of these different values. As I mentioned earlier, we can talk about the radial velocity feasibility, but also in tests, there's going to be a ton of single transits, and EXOFAST v2 can just seamlessly characterize and give you the uncertainties of a single transit system. But then if you go and you get more follow-up data, you can do a detailed characterization, and you can add up all of your follow-up data and model that too. So it really enables and really lowers the barrier of entry for a really sophisticated uniform global analysis by you, the community. So I think this is a really powerful tool that is good to learn. Okay, so this is a list of publications that have already been written with using EXOFAST v2 as the modeling, and I put in bold a couple of systems here that I was not involved in. And in fact, I didn't know about this one until yesterday when I was making this talk, that really just shows that anyone can download this code. It's on GitHub right now. There's a lot of documentation. Have at it and model your system. And then this one was the system that Andrew Vanderberg was talking about in the last talk, the 6-planet system that ended up being quite complicated and broke everything, but we fixed it. Okay, so I want to talk about the hands-on sessions that we're going to go through, or that you get a pick from. So you can pick from one of these 6 topics, and they're roughly ordered in easiest to most difficult. So if you want a more challenging, go for the higher numbers. And then these are far more difficult. So you probably want to, if you're really interested in this, you might want to do it on your own time. But we don't allow those for the group projects. But I just want to go through them real quickly. One project you can pick from is you can use radial velocities from multiple telescopes, and you basically see what the difference is when you fit 1 telescope versus 2 telescopes on various data sets. For number 2, you do basically the same thing, but with multiple transits from multiple telescopes in multiple bands. See what the difference is if you observe with 1 transit or 2 transits in different bands. The effect of maximum steps on the MCMC, so that animation I showed where you get this kind of ragged probability distribution function. If you take few steps and you get a smoother PDF with longer steps, you'll sort of explore that in a more intuitive feel. The long cadence transit data. This is really important for K2 and Kepler, but it's also important for the test full frame images. So you can choose this project if you want to learn more about how to model with the long cadence data and the effects of what happens if you don't. And then here you can explore how important it is that your starting values are close to the actual values, and how far off you can be before things go a little funky. And here you get to explore just fitting the star and the different ways that you can fit the star and how that might feed back into the planetary parameters. And I won't talk about these bonus exercises, but you can see them. If you go to this URL here, it has a lot of detailed information about the walkthrough. And you can also link from, it's also linked from the webpage, the Sagan Exoplanet Archive, or the Sagan Exoplanet workshop page. You can find this link to the walkthrough. If you're really interested in the guts of EXOFAST, I highly encourage you to read that beforehand so you can get the most out of the workshop. There's a lot more than we can cover in the 2 hours of the workshop. So the more you can come prepared and have questions, the more you'll get out of it. Okay, and with that, I'll just leave up this slide here, the summary slide that talks about all of the basic features of EXOFAST, and I'll take your questions. Yep. So the question is, does it work for pre-main sequence and evolved stars? It does. So anything that's handled by the missed isochrones, you can just, it will handle seamlessly. You might have some trouble with the starting values, so you might have to play with those, but that will just work with the missed models. If you have some independent constraints on the mass and radius that you trust more than the missed models, if you decide that the missed models don't really apply there for whatever reason, you can just disable that, and you can apply your own mass and radius priors. The question is, can it fit binary stars? It cannot. That's on the list. There's a long list that I have in my mind of things to do, but it cannot currently do binary stars. So the question is, can it fit Rossler-McLaughlin effect? Yes, it has a fairly simple, it uses the OTA 2005 approximation for the Rossler-McLaughlin, but it can also do a more sophisticated Doppler tomography model for the system too, and we've done that for some of the Kelp systems.
One more question.
Yeah, so the question is, what can it do for single transit systems that we're likely to see in tests? Yes, so it can determine the period. There is a degeneracy between the period and the eccentricity that you kind of have to make assumptions, or you can have some prior on the eccentricity distribution, and then you'll get a correspondingly wide prior on the period, but it will derive a period for you. It will be more accurate if you can give it a good stellar density beforehand, because the stellar density is also degenerate with eccentricity that you just don't know, or if you have the eccentricity from the radial velocity, that will also work. But if you're trying to nail down the period, you probably don't have that either. So yes, it will basically, the more you can give it, the more it can tell you, but it will tell you as much as you can really realistically determine from it.
Okay, let's thank Jason again, and we have the hands on session.